Hello, my name is Michelle Tomczyk, and I'm with Jeremy Levy's group at the University of Pittsburgh. Today I'll be discussing some interesting electronic behavior that we observe in electron waveguides at the lanthanum aluminate strontium titanate interface. Confinement in an electron system creates a manifold of subbands, and tuning the chemical potential changes the occupation of these subbands. When transport is ballistic, each subband contributes a quantum of conductance according to Landauer's formula, leading to a series of steps in the conductance at integer values of E²/h. Applying an external magnetic field can shift the relative energies of these steps, of these subbands, as depicted here. So for example, we can see that this 2 E²/h step at zero field for the spin degenerate states splits into 2 E²/h steps at finite magnetic field. Additionally, when confinement can be tuned in both dimensions, transverse to the direction of transport, then a more complex manifold of subbands becomes available. Quantum point contacts have been used to confine electrons to just one vertical mode, while this split gate geometry is used to tune the lateral confinement and therefore tune the number of ballistic channels that are occupied. However, the length of the ballistic channel is no longer than the width here of the point contact. Creating one-dimensional electron waveguides with long ballistic channels is much more difficult, as many techniques that are used to reduce dimensionality also tend to reduce the scattering length. However, this has been achieved in a few material platforms such as carbon nanotubes and ultra-clean gated semiconductor heterostructures. And so electronic behavior such as quantum interference, tunneling spectroscopy, and magnetoelectric behavior have been studied both experimentally and theoretically in these waveguide devices. Another system of interest for creating electron waveguides is the lanthanum aluminate strontium titanate interface, where our group is able to create long, narrow conducting channels with controllable lateral and vertical confinement. In order to do this, we start with a heterostructure where the lanthanum aluminate layer is just below the critical thickness, so that the interface is still insulating. By applying a positive voltage to an AFM tip and moving it across the surface of the lanthanum aluminate, we leave a path of protons, which then act as a local top gate, tuning the interface through that metal insulator transition. This process is also reversible. By applying a negative voltage on the AFM tip, we can remove the protons and restore the insulating state. And in this way we can create nanoconstrictions and tunneling barriers in these interface nanowires, which are on the order of 2 to 20 nanometers in width. Various devices we've been able to create using this technique include single electron transistors, Fabry-Perot cavities, and electron waveguides. And using these devices we can probe various electronic phenomena such as quantum interference oscillations indicating very long coherence and elastic scattering lengths, quantized conductance plateaus, high mobility extending to room temperature, a strongly correlated phase in which electrons pair far outside of the superconducting regime, and gate-tunable electron-electron interactions. Here I want to focus on how we can use these electron waveguide devices to probe the electron interactions in the system. So in an electron waveguide device, we have these two small barriers here which decouple this nanowire segment from the source and the drain, and this allows us to efficiently tune this nanowire segment with the side gate voltage. In our LaAlO SrTiO based waveguides, we see very nicely quantized conductance plateaus indicating clean ballistic transport through these waveguides. However, not every integer value it shows up very strongly. So looking a little bit closer at one of these line cuts, minus 6.5 Tesla, we see that the conductance plateaus occur at 1, 3, 6, and 10 E²/h, which is reminiscent of a Pascal series like in Pascal's triangle. This behavior is very distinct from the typical consecutive integer steps, 1, 2, 3, 4, 5, that typically appear in one-dimensional electron waveguides. So to better understand this, we take the derivative of each of these line cuts and plot the transconductance as a function of side gate voltage and magnetic field. And so here now, each of these bright bands corresponds to the transition between two of the modes, between two of the the plateaus, and the dark regions correspond to these quantized conductance plateaus. And so now we can see that the plateaus at 1, 3, 6, and 10 e squared over h are due to the successive bunching of 1, 2, 3, and 4 electron states. Additionally, we can see two sets of manifolds, two manifolds of subbands in the structure here. So these closer space subbands are due to the confinement in the y direction, in the lateral dimension across the nanowire, whereas this manifold that's spaced farther apart, these are due to tuning the occupation of the z modes, the vertical modes, in these nanowires, or in these waveguides. So looking a little bit closer now, we see that there are some features that deviate from a single electron model. So for example, at low fields, we see that these two spin split levels don't start splitting at zero field, they start splitting at some finite magnetic field. And this has previously been identified in single electron transistor devices as the pairing field. As the pairing field, sorry. Additionally, at higher magnetic fields, we see that as these opposite spin electron states bunch together, they don't simply cross, they actually lock together briefly before separating again. And so in order to better characterize these behaviors, we plot the positions of the conductance plateaus and on top of the transconductance. And so that's what we see here. And so looking at delta VSG between these first 1 and 2 e squared over h steps as a function of magnetic field, we see that delta VSG increases linearly with magnetic field out at high fields, but across zero field it's flat, and so this gives us a pairing field of about 1 Tesla. Additionally, at higher fields, if we again track delta VSG between now the second and third electron states, we see that as a function of magnetic field, delta VSG goes to 0 for some width of field here, and so the reentrant pairing field width, this locking behavior happens for about 0.15 Tesla. Now the phase diagram for these different regimes has been explored with a density matrix renormalization group calculation for attractive fermions in one dimension. And so to learn more about the whole calculation and the various phases that emerge, please see Binbin Tian's talk on Thursday at noon. But here I just want to highlight 3 phases in particular that appear. So first, at the very bottom of this line cut, we have an insulating waveguide. Then as we cross the first subband, now we have a phase of spin polarized single electron transport. As we cross this reentrant pairing state onto this 3 e squared over h plateau, we enter a regime of electron pair transport, where electron pairs are moving ballistically through the waveguide. When the DMRG calculation was extended to 3 fermions with attractive interactions, then a new phase emerged, a trion phase, in which 3 electron states are bound together, moving ballistically through these waveguides, through this waveguide. Now, a single electron, this can, if you model this as single electrons, uncorrelated electrons in a harmonic oscillator potential in both the 2 transverse directions, then you end up with these 2 sets of modes, as we've seen, indexed by n for the y modes and m for the z modes, as seen here in the wave function calculations. Very precise tuning of the parameters, of the material parameters, can lead to these Pascal degeneracies. However, changing the parameters slightly can easily break the degeneracy. So this is a very fragile state here, and the interesting thing is that we've seen this behavior in not just one, but in fact in actually nearly about a dozen different devices. So here's a representative set, and in this last device, we actually see up to 6 electron states bunching together, leading to conductance plateaus up to 21 e squared over h. And so it's not clear why the system so consistently satisfy, why the system would so consistently satisfy the precise relationship between the parameters that's necessary to achieve these Pascal degeneracies without the effect of, for example, electron-electron interactions, leading to the consistent system-wide tuning of the band structure. And so, in summary, we can create electron waveguides with very clean quantized conductance, very well quantized conductance, characterized by this Pascal liquid behavior. And these features cannot be explained by a single particle model. However, electron-electron interactions can predict both the reentrant pairing behavior as well as larger electron bunching, such as the trion phase. But it remains an open question as to why this Pascal degeneracy is so prevalent that while we don't see it in every device, we do see it in a dozen different devices. And so, in summary, this behavior really highlights the unusual and interesting aspects of strong attractive interactions in this superconducting semiconductor system.